Hello, this is Jude Socrates, and our video for today is about systems of linear equations and the fundamental matrix spaces. Now, you might be thinking, haven't we been talking about systems of linear equations for the last few videos? And of course, you're correct. But you also should remember that a few videos ago, we introduced the concept of the four fundamental matrix spaces. And I said, we're going to study them, we're going to find the basis for them, but you're going to have to wait just a little bit to see why they are important. So, in today's video, I am going to be keeping that promise. All right, so what we're going to do in this video is we're going to learn why each of the four fundamental matrix spaces is important, and we will also study a kind of system that we've actually seen before, but we haven't given a name to, and that is a dependent system. Now, we've seen the word dependent when we talked about sets of vectors, when we called them either linearly independent or dependent. So now we are going to talk about dependent systems of equations, where that means simply that we encounter a row or more of zeros in the REF of the augmented matrix for that system. So let's start with two of the four fundamental matrix spaces. We are going to see how the column space and the null space fit together when we are solving systems of linear equations. So this is called the column space test for consistency. The matrix equation AX equals B is consistent, meaning of course it has at least one solution, if and only if B, the vector we find on the right side of the equation, is a member of the column space of A. Now, why is that true? Well, the matrix product AX, we said, is a linear combination of the columns of A with coefficients from X. So remember, we have x1 column 1 plus x2 column 2, and so on. So if we want that to add up to B, then B is a linear combination of the columns. And of course, that is the definition of the column space. So now, furthermore, if AX equals B is consistent, suppose that x of P is any particular solution, as we call them in section 1.4. Then a vector x is a solution to this system, if and only if it can be written in the form x equals xp plus xh, where xh is a member of the null space of A. So this part we've actually seen before, except I didn't exactly point a finger to it. So now when we see our example, we're going to see that that is indeed the case, that we can separate the solution vector into an x sub p, a particular solution, and an x sub h, a member of the null space of A. So consequently, if x1 and x2 are any two solutions to AX equals B, then x1 minus x2 must be from the null space. And we can see that from this equation. We have any vector x as a solution if it's in the form xp plus xh. So if we have x1 is xp, the same xp plus xh1, let's say, and x2 is xp, the same xp as we used for x1, plus xh2, then when you subtract them together, what you get is that x1 minus x2 will be on the left, and xp will cancel from the two equations. And we're going to get xh1 minus xh2. But the null space is a subspace. So xh1 minus xh2 is still going to be a member of the null space. So because of that theorem, it tells us that if you put together all the solutions to AX equals B, we will have each of them looking like x sub p, a fixed solution, plus a member of the null space. So I hope you remember back when we started out, when we talked about lines and planes in R2 and in R3. We talked about lines and planes that don't pass through the origin. So we took a line, let's say in R2, and we translated it, we shifted it away from the origin by adding a fixed vector to each of the vectors of that line. So we can think about the solution space to our equation AX equals B also as a translate of the null space. And in general, we can do that to any subspace of Rn. So if W is a subspace, we can write B plus W to be the fixed vector B plus W, where W is from the subspace. So we call this a translate of the subspace W. So our solution space X is a translate of the null space by the particular solution X sub B. Who is this X sub B? Well, we have been asking for the simplest solution to a linear system, and that is where we set all of the free variables equal to 0. So we can use that as our XB when we do our examples. Get it? Wow, that's a big system. Ha, just kidding. Yeah, it is a big system. We have 6 variables, x1 through x6, and we have 1, 2, 3, 4, 5 equations. Okay, so this is a 5 by 6 system of equations. And what are we going to do? Obviously, we're going to try to solve the system. So we're going to see if it's consistent, and if so, find all the solutions. And of course, what we want to do is express the solution space in the form xp plus the null space, as we saw in the column space test. Okay, so of course we're going to find the REF. So let's take the coefficients and we form the augmented matrix as before. So what did I say? First rule of math, make sure that you copy down the problem correctly. So check that all the numbers in each of the five equations match the entries in our augmented matrix. So if a coefficient or a variable is missing, that should be a 0. Okay, so let's find the REF. Okay, so of course, as usual, we have to erase the vertical bars, and then we do our compute, matrices, and REF. Okay, so there is the REF. We have 2 rows of zeros. So we're going to see in a few minutes what is the meaning of those 2 rows of zeros. And it is consistent. Okay, so we don't have 0 equal to 1. Each of these remaining 3 rows contains a leading 1. We have it in column 1, column 2, and column 4. And so our system is consistent. And let us now write down our solution vectors. So as usual, we have an equals here separating the right column. So let's review. We will have x1 plus 2x3 plus x5 minus x6 equal to 3. So solve for x1. We will have 3 minus 2x3 minus x5 plus 2x6. So we're going to write down x1, x2, and x3 for our solution vector. So my apologies, I think I said x3 instead of x4 just now. So anyway, we said x1 is 3 minus 2x3 minus x5 plus 2x6. So there we have it over here. x2 is negative 3 minus 5x3. This is 4, 5, minus 4x6. So that's what we have here. x4 is negative 8 plus 3. That is fifth column, x5 minus 7, x6. So those are our 3 equations for x1 and x2 and x4. x3, x5, and x6 are free. So let us erase x1 and x2 and x4, and we keep x3, x5, and x6 in our solution vector, and we will copy these three into these components. Okay, so we have our solution vector over here. This equation describes all the solutions to ax equals b. So back in chapter 1, we would be very happy once we get to this point. We're done. But what we want to do now is to express our solution space as a translate of the null space. So we need xp plus xh. Now you might be thinking, well, that's only two vectors. Why do we have four vectors over here? Well, this is going to look a lot like what we did when we solved the homogeneous system and we separated the x3s from the x4s from the x6 and so on. In this case, though, we will separate the constants which are by themselves, the 3, the -3, and the -8, and put those in their own vector. So 3 goes in the first component, -3 in the second, and the -8 goes into the fourth component because that is from x4. So our x3 is 0 and our x4 is -8. And then the other two free variables are, of course, just zeros. Okay, so that first vector is our xp. I hope you recognize it. It would be the solution that you would get if all of the free variables are 0. You will just get x1 is 3, x2 is -3, x3 is 0, it's free, x4 is -8, x5 and x6 both 0. That's our xp, the simplest solution. Why do anything more complicated? Okay, so now we want the x3s together in one vector. So we have -2x3 in the first component. And then in the second, we have a -5x3. Third component is a free variable, so we do write x3 there. There is no x3 in the fourth, fifth, or sixth components. Once you have your free variable, it doesn't appear to the right. So those are all zeros. Okay, our next free variable is x6. So we have 2x6 in the first component. In the second, we see -4x6. In the third, that's x3, so we should put 0 there. In the fourth, we have -7x6. And then we have, x5 is a free variable, so that's a 0. And our x6 is in the last component. And did you just notice I skipped over x5? My bad. So, fortunately, it's commutative. Haha. So I'll just scoot that over there. Now let's attack x5. So we have -x5 over here. In the second component, I see, oh, that's why, because there is no x5 in the x2 component. Oh yes, look at that. We have a 0 in our column 5 where the leading variable is x2. That's what threw me off, but that's okay. It's commutative. So we have 0 x5 in the second component. x3 is a free variable, which is not x5. In the fourth component, we have 3x5. 3x5. And then in the fifth component, that's where x5 goes. And x6 is 0. Okay, so that's great. But we're going to go, of course, one more step. We are going to factor out three variables from these three vectors. So we'll make a copy, and they should look familiar. take all the x3s out. So erase that. That x3 turns into a 1. Zeros stay zeros, of course. Take out that x5. Don't forget to put a -1 there or it will look weird. And then here the x5 is gone. And here that x5 turns into a 1. x6 take outside. x6 is gone. x6 is gone. And that x6 is gone. And we have a 1 over there. Okay, so if that is our xp, these three vectors together should be our xh. So xh is actually three vectors added together, one for each of the free variables. So let's take a look now and see, why is this sum from the null space? Alright, so to do that, let's review the homogeneous system of equations. I have highlighted the portion of the matrix corresponding only to A, and we're going to copy that. So let's scoot down and let's put that over here. Alright, so that is the portion of the REF that is only from x1 through x6. Okay, so let's review. Forming a basis for the null space of the matrix. We have 1, 2, 3 free variables. So remember, we will need one empty vector for each of the free variables. So let's put that over here. So we have 1 and 2 and 3 empty vectors. Okay, so we'll just think of those zeros as empty. Okay, so our free variables are at x3, 5, and 6. So x3 will turn into a 1. The rest to the right of it will be 0. So yeah, let's empty the first two. And then we have x5. So let's empty the first 4. 1, 2, 3, 4. x5 should be a 1. To the right of it will be 0. And then the third should be all zeros except for the last one. So let me copy that last one and make that 0, 1. But we also said that everything below the trailing one, I said that right the first time, the trailing one should be a 0. So below that trailing one, we have a 0 here and a 0 here in the third component. Let's put commas here so we can see them demarcated as usual. And below that trailing one, that should be a 0. So there you go. We normally write it vertically, but we don't have space here. Okay, so where do the 2 and the 5 go? In our first vector, they become -2 and -5. Does that look familiar? That's exactly our first vector. Okay, our next free variable is x5. That goes into the second vector. We have 1, 0, -3. Aha! That explains why I got confused. So -1, 0, +3. Is that exactly what we have there? Okay, last one. -2, 4, 7 becomes +2, -4, and -7. All right, so that is exactly what we get in our third vector. So there you go. These three vectors form a basis for our null space. And so that linear combination is each and every member of the null space of A. Aha. Okay, so before we move on, let me point out that in the REF of our augmented matrix, we saw 2 rows of zeros. And that's exactly the kind of system that we're going to study next. So we will dig deeper into this example. We will call such a system a dependent system. Why is that a good name for a system that has rows of zeros? how do we get a row of zeros? So this means that when we do linear combinations, row operations, I should say, on the augmented matrix, if we do it step by step instead of instantly like this, almost looks like magic, at 2 points in our REF, we will combine 2 rows and suddenly a row disappears. It becomes all zeros. So that should tell us that if we rewind all of those operations, it would be possible to express one of these rows as a linear combination of the other rows. Now, does it mean that it's the 4th and the 5th rows that are linear combinations of the rows above them? Of course not, because we are allowed to swap rows when we are doing our row operations. So therefore, we don't really know which rows combined together will add up to 2 of these rows, because we have 2 rows of zeros. So we are going to find out how to find which are the redundant equations. If you get all zeros, it means that those equations could be satisfied if the other equations are already satisfied. Okay, so let's formally define this. A linear system is a dependent system if the REF of the corresponding augmented matrix contains at least one row consisting entirely of zeros. Otherwise, we call the system an independent system. So let me point out that if you have an overdetermined system, then you will run out of leading ones. For example, if you had 5 equations but only 3 variables, then the maximum number of leading variables that you're going to get is 3. Maybe all the variables are leading variables. But if you only have 3 leading ones, then you're going to get 2 rows of zeros. So therefore, if you have more rows than you have columns, more equations than you have variables, then you are guaranteed to have a dependent system as long as it's consistent. Okay, we still want to look at only consistent systems. Inconsistent systems are practically useless. So this is analogous to underdetermined consistent systems. If you have more variables than you do equations, then we know that you will get at least one free variable in your REF. Okay, so our next job is now to find out which of the original equations of our system of equations are redundant. The trick is not to look at the original system, but to look at the transpose of that system. So we have a minimizing theorem for consistent dependent systems, much like our minimizing theorem for a set of vectors. So suppose you have a linear system represented by an m by n plus 1 augmented matrix. So let's call that matrix B. You have our matrix A on the left and the right side, the vector B, as usual. And let's assume it's consistent and dependent. Okay, let's say that the rank of B is k. In other words, there are k leading ones in our matrix, in our REF, and k is less than n. So in other words, there are rows of zeros. How many? M minus k rows of zeros. Take the transpose of this augmented matrix. B transpose, by the dimension theorem, we know that the rank of the transpose is the same as the rank of the original matrix. So B transpose will have rank k as well, but this time we will have m minus k free variables, not rows of zeros, but free variables. Remember that a row turns into a column, so if you have only k leading ones in the REF of the transpose, that means you have m minus k free variables. Each of these columns containing a free variable corresponds to a row of the original matrix. Okay? These rows come from equations, and these are our redundant equations. Each of these redundant equations can be expressed as a linear combinations of equations above it. Why? Because we know that if you have a column and it is a dependent column, it depends on the columns to the left of it. So because we're now dealing with rows, it means that that row is going to be a linear combination of the rows which are above it. And as in the minimizing theorem for vectors, we can find the coefficients that we need to express that equation as linear combinations of the equations above it. All of these redundant equations can be eliminated from B. And so we have fewer equations, but the new system B prime is now independent. It will not have a row of zeros in the REF. It will have the same rank as the original matrix, and the solution set of that shorter system will be the same as the solution set of the original system. Okay, so let's apply that to our previous example. We know that our system is consistent. Here's the REF, and we have two rows of zeros. Okay, so two of these original equations are redundant. Who are they? Okay, the theorem said we have to get the transpose of the system. So compute matrices transpose, and there it is. Okay, and then it said that we need to find the REF of that transpose and look for the free variables. So let me scoot up here and let's go compute matrices REF. Ooh, okay. So we have leading variables at column 1 and column 2 and column 4. Okay, so our free variables are in column 3 and in column 5. Okay, so if we were back in the old minimizing theorem, it will say that the third column is 4 times the first column plus 3 times the second column. So these are the original columns. This third column is 4 times the first plus 3 times the second. Should we believe that? 4 times 6, 24. 3 times minus 7, minus 21. 24 minus 21, 3. 4 times negative 2, minus 8. 3 times 3, 9. Minus 8 plus 9, 1. Of course it works. The REF doesn't lie. But what does this mean? It means that this column, which came from this row, aha, so let's highlight this row. This tells us that row 3 of our original system is a linear combination of the first two equations. Okay, so what I'm saying is what we call in mathematics abuse of notation. We don't literally add equations together. What we mean is take the left side of this equation, multiply by 4, take the left side of the second equation, multiply by 3, add them together, you will get the left side of the third equation. That takes too much time to say because that's only half the equation. Now you also have to take 4 times the right side of the first plus 3 times the right side of the second to get the right side of the third equation. 0 plus 6 equals 6. So of course what we mean is take the first equation, multiply both sides by 4, take the second equation, multiply both sides by 3, and you get the third equation. In shorter notation, we would say that equation 3 is 4 times equation 1 plus 3 times equation 2. Okay, so let's write that down. Equation 3 is 4 times equation 1 plus 3 times equation 2. We have a second redundant equation, which is in column 5, and of course that comes from row 5 of this original system. Our coefficients are 0, 1, and 2, so be careful with that 0. The only non-zero coefficients are this 1 and 2. 1 corresponds to this leading one, which is in column 2, so that means you want 1 times equation 2, so we just write it as equation 2, and the 2 here corresponds to this leading one, which is in column 4, which means equation 4. So we want to add 2 times equation 4. Okay, so if we add equation 2 to twice equation 4, we should get equation 5. Let's check. Negative 7, twice of 4 is 8. 8 minus 7, 1. 3, twice of minus 2 is 1. 1, twice of 3, 6, plus 1, we get 7. And so on. So we get the last row is the second row plus 2 times the fourth row. Now, of course, if you still don't believe me, I don't blame you. We can do it with our augmented matrix here. Let's take the second row, and then we will add twice the fourth row. And what do we get? We get 1, 1, 7, blank, that's a 0, 1, 2, 0. Just as I said it would be. Okay, so if you've been following along the sequence of videos, this is at the end of chapter 2. So it's a great place to wrap up all 4 fundamental matrix spaces into one scenario, which of course involves systems of linear equations. Now, I'm going to tell you something. This is not part of chapter 2 because I just thought about it the other day. Too late for the 4th edition, but that's okay. It's great to always keep finding new things, new interesting discoveries in linear algebra. It's what keeps me alive. So, what is the scenario here? Suppose you have a set of vectors, v1 to vn, from Rm, and you make the span of that set of vectors. That's a subspace. Let's give it a name, call it W, as usual. That's a subspace of Rm. And we need a right side of the equation, so we will have a random vector b from Rm. Now, as usual, we will form the m by n matrix A, which we called the matrix of S, where v1 through vn are the columns of our matrix A. As usual, let's review. What are the 4 fundamental matrix spaces of this matrix A that we just made? The column space is the span of the columns of A, but we call the columns v1 to vn. In the definitions that we saw in, 2.3, we called them c1 to cn. But this time, we made the vectors first before we made the matrix. Okay. So that's the column space. The row space is now the span of row 1 through row m, the rows of A. And again, why is it m rows? It's because each of these vectors is from Rm. So we write it vertically. There are m components. There will be m rows in our matrix. So that's the row space. The null space of A is the set of all solutions x from Rn, where Ax is the 0 vector from Rm. And finally, the null space of A transpose is the set of solution vectors y from Rm, where A transpose times y is the 0 vector from Rn. So finally, what is the significance of each of these matrix spaces in the scenario that we just described? Let's start with the easiest one, W perp. The orthogonal complement W perp of W is exactly the same as the null space of A transpose. Okay? So remember when we talked about orthogonal complements, we said that if you have a spanning set for W, you have to put those vectors into the rows of a matrix. Or if you insist on putting them into columns, just like we did in the scenario that we just described, you have to flip that matrix first, get the transpose, and then you look for the null space of that matrix. Because you want each vector to be orthogonal to the original spanning vectors, that means that the dot product has to be 0, and that means that the matrix product with each row has to give you 0. That's exactly what the null space is. All the vectors so that when you multiply it with the matrix, you get the 0 vector. What did we just do in this video? We talked about the matrix, the column space test for consistency. Okay, we said that the equation AX equals B is consistent if and only if B is from the column space of A, but that's exactly the span of S, our vectors, which we called W. If this happens, if our equation is consistent, then the solution space has the form XP plus the null space. Okay, so we have the column space and the null space of A, the original matrix A, not the transpose, together in the column space test for consistency. Who is this XP? It's a particular or a fixed solution to AX equals B. It basically means that A times XB has to be B. Finally, for the row space, that's why we talked about dependent systems of equations. Okay? Instead of looking at the row space of A directly, look at the augmented matrix where we call it B. It's A on the left and our vector B on the right side. And let's assume it's a consistent system. So the row space of this augmented matrix is the column space of the transpose. So what did we do in our last example? We took our augmented matrix and then we flipped it over because we had to look for which equations are redundant. What's that? It's just a minimizing theorem. You look for the REF of B transpose, which is what we did, and you look for the free variables. The free variables in the REF of the transpose correspond to the equations, the rows in the original system, which are redundant. And each of these redundant equations can be expressed as a linear combination of the equations which are above it. All right, we have reached the end of our video. This is Jude Socrates, and I thank you for watching this video. As usual, you will find me on Facebook, and you will find the 4th edition on Facebook and also at candlehunt.com. Until our next video, enjoy the rest of the day.